So welcome back, everybody. Can you hear me? And so somebody asked me that I give OneNote a try last class, so I thought I would do that this class. I actually did upload the whiteboards, but I haven't linked them yet into the homepage. And I also, shoot, that's not working very well. Let me see. Let's do this. Okay, I guess I have to use it in this orientation. Are there any questions, problems, difficulties? Oh, another thing that I actually plan to do is various people, I was happy to see that some discussion has started in the on Canvas, and various people have said I don't have this in my background or I don't have that in my background, and I actually will put together a sheet of textbooks on different related subjects that I like and put it on Canvas. You know, what are some good books on functional analysis? What are some good books on, I don't know what, real analysis, geometry, partial differential equations. Wow, I guess maybe some people are watching asynchronously, but so things have really collapsed in terms of online. So registration is up, but online attendance is small at the moment, today at least. Let's see how it goes. I guess last class we started, we talked about the Kantorovich duality theorem. And my first agenda for today is to, so let me write the Kantorovich duality once more. Oh, I can tell you some funny story too. So I guess we wrote it in this form, max integral b d gamma over gamma with fixed marginals is equal to min integral u d mu plus v d mu minus over all u and v bigger than b. And a virtue of the Rockefeller-Roche proof of this duality was that we actually showed that the minimum was attained as part of the proof. So that was kind of nice. So also there have been some various complaints about my handwriting, so which I apologize for. I will try to, I'm trying to use a larger pen stroke, which Cameron recommended, and I'm trying OneNote, and hopefully that will, maybe that will improve the situation. But I can also tell you a story from my freshman physics class. So at some point in the middle of my freshman physics class, one of the, which was taught by a guy doing low temperature superconductivity, and he used to kind of write very quickly on the blackboard, and it was he'd scribble very quickly on the blackboard. At some point, one of my classmates raised my hand and said, "Professor Harrison, why don't you slow down? Nobody can read your writing." And Professor Harrison responded and he said, "Oh," bouncing up and down, "I don't write it so as you can read it. I write to pace myself." Anyways, I don't write to pace myself. I guess writing does slow me down, so maybe it does. Maybe I do pace myself in that sense. So one of the things that we wanted to, so somehow at the end of last class, we talked about, well, we had these, so somehow when you take the optimal solutions to these two problems, you have a non-negative function, b of xy minus u of x minus vy. Sorry, I guess that's non-positive. Okay, well, that's fine. And equality holds gamma almost everywhere. And so if you, where u is different, I mean, so you have this non-negative function, and obviously it's attaining its maximum gamma almost everywhere, so you should expect these calculus conditions to hold, right? So dxv of xy should be duxy gamma almost everywhere. if U is differentiable. So gamma almost everywhere such that X is a point of differentiability for U. And similarly, at a maximum, we'd have the second derivative of B minus the second derivative of U should be non-positive definite. It's a symmetric matrix, gamma almost everywhere such that X is in the domain of second differentiability of U. And so obviously, what we would like to know, not only that the U and V that attain this minimum exist, but we'd like to know that they're differentiable almost everywhere. Would be very nice. And even second, twice differentiable almost everywhere would be even better. Because somehow this first condition here is the key to showing that the optimal gamma that the support of gamma is contained gamma almost everywhere in the graph of some mapping G. Right. And then that map, so G here would be a map from M plus to M minus. And when this is true, then G would solve the problem in the sense of Monge and not just the sense of Kantorovich. So in other words, Monge insisted that all of the output from a mine at X go to a single factory instead of Kantorovich, who allowed the output from mine at X to be distributed over a whole space of factories. So in some ways, Kantorovich's solution is a bit analogous to a randomized solution in game theory, and Monge's solution is a bit analogous to a pure solution in game theory where Monge was forcing the strategies to be non-random, non-probabilistic. And we saw that we looked at this particular example when B of xy was the inner product with x and y. Then maybe I should do this in a different color. So for this particular example, with m plus and minus equal Rn, then dvxy in that example was y. And the second, and the second derivative, right. So in fact, let me write this in the form db of x is less than that. And then the second derivative, of course, with respect to x of y is 0. So that's the 0 matrix now. And so in this particular example, this second inequality is telling me that the function is trying to be convex, and the first inequality is telling me that all of the mass at a point x is going to be shipped to a single destination given by grad u of x. And that'll be, and the wonderful thing about convex functions is that convex functions are in fact twice differentiable almost everywhere. So this is a theorem of Alexandrov. We can allow plus infinity as a value if we like. And so at least for this particular choice of cost, we're in good shape with respect to these the existence of these two derivatives, at least. So a corollary is desired derivatives exist Lebesgue almost everywhere. And hence mu plus almost everywhere if mu plus is absolutely continuous. I don't know what's, I'll use HN for Lebesgue measure on Rn. Right, absolute continuity means that mu plus would vanish on every Lebesgue set of measure 0. And so let me let me try to motivate Alexandrov's theorem a little bit. This is from the 30s, about 1933. So in one dimension, a convex function has a non-decreasing derivative. And most of you have probably seen that in real analysis that non-decreasing functions are differentiable Lebesgue almost everywhere. That's, I guess, Lebesgue's theorem, one of Lebesgue's theorems. So in some sense, this theorem of Alexandrov is the generalization to Rn of Lebesgue's theorem. And let me mention a if you want to see it, I'm going to sketch the idea of the proof of Alexandrov's theorem. I'm going to gloss over some details. If you wanted to see a detailed proof, you can find one in the appendix of Evans and Garayapi's textbook, Measure Theory and Fine Properties of Functions, which will be on my reference list. But let me mention a related theorem, which is a theorem of Rademacher. Maybe, well, maybe I should say what a Lipschitz. So recall U on a metric space is Lipschitz if there's a constant such that ux minus uy is less than the constant times the distance for all x and y. And I can put absolute values here. It doesn't really matter since x and y are interchangeable in this definition. And sometimes we'll denote the smallest such C by lip U. And now there's the theorem of Rademacher. In Rn, but it extends to, since manifolds have coordinate charts and differentiability is a local notion, it would extend to manifolds as well, which says Lipschitz functions are differentiable almost everywhere. And this is it's a pretty useful theorem. It's a, what do you say? So Lebesgue's theorem said that non-decreasing functions were differentiable almost everywhere. So non-decreasing functions are functions which have their distributional derivative as a non-negative measure. And so in one dimension, Rademacher's theorem is a lot weaker than that because Lipschitz functions are functions whose distributional derivative is an a measure with an L infinity density. So in one dimension, you don't really need an L infinity density, an L1 density, or even a measure density would be enough. But this is Lebesgue again. I'm using H instead of L because it's short. For me, it's short for Hausdorff measure. And so Lebesgue measure is the top dimensional Hausdorff measure, but Hausdorff measure can also be defined on smaller dimensions than n. So you can talk about the one-dimensional Hausdorff measure of a curve in Rn, or the two-dimensional Hausdorff measure of a surface, and so on. And so basically what I wanted to motivate is that you can understand Alexandrov's theorem about second differentiability of convex functions as to be a consequence of Rademacher's theorem. There's sort of a clever geometrical construction that allows you to do this, but I should be careful what I mean by twice differentiable, because I guess it's I guess I should say Well, so what's the problem? The problem is that the first derivative of my convex function exists Lebesgue almost everywhere. And you might worry about what does it mean for the second derivative to exist at a point where the first derivative doesn't exist in an entire neighborhood. So, so I guess I don't quite mean it's twice classically differentiable, but I mean that a derivative exists in the sense that it's a second order Taylor expansion. So note. So let me say, I can cure this by saying approximately twice differentiable, which is approximate differentiability is a notion from measure theory, which probably most of you are not familiar with. But if you're familiar with it, then what I say is true. But another interpretation, another way to cure this problem is that convex functions have a second order Taylor expansion Hn almost everywhere. In other words, i.e. there's a matrix, an n by n matrix, let's call it Q maybe, such that ux is given by ux naught plus derivative of u at x naught, x minus x naught, that's the first order Taylor expansion, plus x minus x naught q times x minus x naught plus lower order terms. So something that's little o of x minus x naught squared as x goes to x naught. And alternately, so this is actually, so the second definition which I'm giving is stronger than the first definition. Grad u of x equals du of x naught plus q of x minus x naught plus little o of x minus x naught but now for this definition, I need, so now I'm saying that the gradient of u actually admits a first order Taylor expansion, but the problem is that the gradient u is only defined on a set of full measure. There'll be points like the origin for the absolute value function where there are lots of supporting hyperplanes, lots of gradients. And so, so then it would still be true, but it would only hold at points where it's actually differentiable. So at points of differentiability where grad u is defined that tend to x naught, then you'd still have this first order Taylor expansion. So that's what Alexandrov's theorem is asserting. Other questions about the claim? So I can maybe just sketch the idea of the proof. So what's the idea of the proof? Oh yeah, so even before, maybe I defend, let me defer the idea of the proof for a second. So, and let me recall. We showed that if u was a function on R, possibly taking plus infinity as value, that the B subdifferential of u is B cyclically monotone. We showed that last week. And at the time I said, actually, it's if and only if, but we didn't show the converse direction. So let me show it now. And then I'm going to use that in my idea of proof of Alexandrov's theorem. So this is somehow the easy direction. So let me take a bunch of points, x1, y1, up to xk, yk in the B subdifferential. And recall what that meant was that u evaluated at any point was bigger than u at xi plus b at that point, comma, yi minus b of xi, yi. So this was true for every blank. And so let me take the blank. So that's for every dot in M plus. And this was the subset of the product space. And so now let me, if I take the dot to be equal to xn plus 1, say, xi plus 1 rather. So, so I have u of xi plus 1 is bigger than u of xi plus b of xi plus 1 yi minus b of xi yi. And then I want to, so by the way, since for the first thing to hold, this is a finite number. This is less than infinity because I don't want to allow u to be identically infinity. And so there'll be some value of dot where this is finite. And so for this to hold, since b is real valued, this guy has to be less than infinity. Okay, so now I have this the inequality on the next line holding for all I, and I just sum on I. And when I sum from with the convention that xk plus 1 is equal to x1, so cyclically, when I sum on I from 1 to k, the sum of these terms is the same as the sum of those terms, and so they all drop out. And so then I get 0 is bigger than the sum of bxi plus 1 yi minus bxi yi. And so that basically shows if I do a cyclic permutation with the x's with respect to the y's, that I get the inequality I wanted for B cyclical monotonicity, namely sum of bxi plus yi is bigger than, is less than B of xi yi. And if I look at more general permutations, any permutation can be written as a product of cycles. And so I can apply this several times to get a more general permutation. So actually, people often take this to be the definition of cyclical monotonicity because more general permutations are products of cycles. So we can sort of forget about them and take for every finite sequence of points this inequality to be the definition of B cyclical monotonicity. Okay, so now I have this. And so that tells me in particular, I want to come back to Alexandrov's theorem, and I want to reduce it to Rademacher's theorem. It tells me in particular that if I look at our special example where B is bilinear, and so then, so now I switch colors again. Then this inequality turns into saying that y is like the gradient of u, and I have a first order Taylor expansion. So in that case, we usually just write this as du, which is the set of point slope pairs of supporting hyperplanes of graph U. Right, so it's exactly the set of xy such that u of anything is bigger than u of x plus, in this bilinear case, it turns out to be the anything minus x comma y. And so this is, again, like it's like a first order Taylor expansion. And the peculiar thing about convex functions is that so what's the picture? The picture is a convex function can look like this. And so at a point like this, you would have a supporting hyperplane that looks like that. At a conical point, you might have two different supporting hyperplanes with different slopes. And so for this x naught, both of the slopes corresponding to these y's would be in the subdifferential. Is it clear? Other questions? And so when we want to show second differentiability, when we want to show U has a second order Taylor expansion at some point x naught, it's like showing that the gradient of U has first order Taylor expansion, which is like showing that this set here has a well-defined tangent plane. Being a Lipschitz submanifold of dimension n in R2n with a well-defined tangent plane. HN almost everywhere. So, and again, the picture, so somehow the picture is clear in one dimension, I hope. So in one dimension, you have a non-decreasing, the set of point slope pairs which support a convex function is some non-decreasing curve in the plane. And sorry, I guess this was supposed to be a one-dimensional picture. Well, the nice thing about this proof is that the one-dimensional picture works in n dimensions as well. So this is, let's say, x, and this is y. And I'll just write n, and we can think of n being 1 for the moment. But now if I do a change of variables, so let me go to new variables, and this works in Rn. So my new variables will be, let's say, z, which is like y plus x over root 2 maybe, and w, which is y minus x over root 2. So somehow if you turn the picture by 45 degrees, then I can't turn my computer on the screen share by 45 degrees. But so the point is that in one dimension, you can see by inspection that W is a Lipschitz function of Z with Lipschitz constant 1, because the steepest slope parts of W correspond to the parts that are vertical for Y as a function of X. And the flattest parts of W are the ones that are steepest in the other direction are the parts that correspond to Y being flat as a function of X. And so for W as a function of Z, the slope oscillates between plus and minus 1. So it's a one Lipschitz function. So it has a tangent plane almost everywhere. Okay, that's good. So somehow the there's a tangent plane here, and that's going to tell me the second derivative of my convex function, whose first derivative I've drawn. There's also there's a tangent plane here that would correspond to infinite slope. In fact, there's a whole bunch of points with that tangent plane having infinite slope for Y as a function of X, but they all project to the same X. And so the points like that turn out to be measure 0 for Y as a function of X. And points like this, which are most of the points, almost all of the points for Y as a function of X have a well-defined tangent plane. So somehow that's the idea of the proof of Alexandrov. And so so we define W and Z as above. And then we want to look at the difference between, say, W. So step 1, the subdifferential is cyclically monotone. so in particular, if I choose 2 points, x0, y0, and x1, y1 in the subdifferential, what cyclical monotonicity says for 2 points is that the inner product of the change in x with the inner product of the change in y is non-negative. So now let me make the change of variables to w and z. I want to compute, and I'm going to define, so then I'll have points, zi, wi, and I'm going to define delta z and delta w analogously to the above. And I want to compute, let's say, delta w squared minus delta z squared. And delta w squared is something like y squared plus x squared over 2 minus root 2 inner product of y with x, delta y over plus delta x squared minus 2 inner product of delta y with delta x, minus a similar thing, delta y squared plus delta x squared over 2, and this time it'll be plus instead of minus. And so these terms cancel each other out when I do the subtraction, and these terms add up. But so this is, you have to shake this inequality, and you see that this, and you'll see that this turns out to be the 2-point case of cyclical monotonicity. So this turns out to be non-positive, and what that tells me is that when I choose any 2 points on my graph, that the delta w squared, or delta w, is less than delta z. So that tells me delta w is a 1 Lipschitz function over z. Hence, differentiable almost everywhere. By Rademacher. And so, since we were arguing about this is essentially something like the graph of x du of x. It certainly includes the graph of x du of x. And so, since we've shown the differentiability of this almost everywhere, we've shown the second differentiability of u almost everywhere, or the first differentiability of its gradient. Is it clear? Are there questions? Okay, so now we know that convex functions have 2 derivatives almost everywhere in this sense of Alexandrov. Thanks for the thumbs up, Joaquin. So if we go back to our original problem, this kind of development that I've shown for applies to the the function x dot y turns out to apply to a much broader class of functions b as well. So for a much, basically if support of mu plus and mu minus are compact and b is twice continuously differentiable, then I can find a minimizer u and v which are as smooth as a convex function would be. So in other words, which have two derivatives almost everywhere. So for more general B, U inherits some smoothness from B. That's how to think of this anyways. So for example, B Lipschitz implies U Lipschitz. And there's one other notion, which semiconvexity, which I guess I should introduce. So, so this is a definition. Let's say a function x on Rn, a function u on Rn. Is semiconvex if there exists a constant such that ux plus a large multiple of 1/2 x squared is convex. And so you can imagine that this works. There's a local version of this definition where you would just say U is convex on a small ball if there is semiconvex on a small ball if there's a large constant such that U plus cx squared is convex on the ball. So I could make this locally semiconvex if for every b epsilon of x naught, there exists a c which would now depend on epsilon and x naught, such that this is the convex on the ball. Or you'd say if it's locally convex at x naught, you'd say that locally semiconvex at x naught if there exists a constant, blah blah blah. And so this notion makes sense on manifolds as well. Local semiconvexity is well defined on smooth manifolds by going to coordinate charts. And the point is that, if you change charts, the constant C may, if you make a smooth change of charts, the constant C may change, but the fact that there exists some C won't change. And so, and this is actually not too hard to check, but let me illustrate where these principles come from. But okay, before I do that, somehow there's always something to do before. So I should say U can be chosen to inherit. So in other words, nobody said anything about the. No, we haven't yet discussed whether this minimizer is uniquely attained yet or not. There could be more than one. In fact, it isn't uniquely attained because any U and V that minimize it, you can always add a constant to U provided you subtract the same constant from V. And because the measures mu plus and mu minus have the same mass, adding a constant to u doesn't affect the value of the thing if you subtract the same constant from v. But so the minimizers are certainly non-unique up to these additive and subtractive constants, but they might be non-unique in a more serious way. And so the claim is that you can always choose one that's that inherits some smoothness from V. And so let me so in the same way that cyclical monotonicity was special to the notion of, ordinary cyclical monotonicity as opposed to bicyclical monotonicity was well adapted for convex functions. Bicyclical monotonicity is well adapted to a more general kind of function, which is a so-called B-convex function. So let me, and the point is that I can always choose a pair of minimizers, which are B-convex and where U and V are in duality with each other, in the same way that for the bilinear cost, you can always choose a pair of minimizers U and V such that V is the convex dual function to U. So in other words, the slope of, if the slope of U at X is Y, then the slope of V at Y will be X. So in other words, under interchange of location and slope, there's a so-called convex duality. So to do this, let me introduce what's sometimes called the B transform. So if I have a function on U, possibly taking infinity as value, but not identically infinity, I define its B transform to be a function on M minus. That's supposed to be a superscript B. And it's basically going to be given by the supremum over all x and m plus of bxy minus ux. And similarly, if I have a function v on m minus, its transform, I could call it the B tilde transform maybe, is going to be a function on m plus defined by sup over y and m minus b of xy minus dy. So the B transform takes functions on m plus to functions on m minus. The B tilde transform takes functions on m minus to functions on m plus. And so the remarkable fact, so this transform interacts with, in a nice way with, so there are a couple of remarkable facts, but this transformation interacts in a nice way with the problem of minimizing the Kantorovich dual problem. So it's attained by a pair U of V such that U is the B tilde transform of V and V is the B transform of U. So that's the claim. And the proof well, let's see. I already know the min is attained. I just want to show that it's attained by a pair of functions of this form. Otherwise, I need to go through another compactness argument. So I'm going to let UV minimize. And then I claim U transform also minimizes. Does at least as well. So in fact, I don't even need this to be a minimizer. So let U and V satisfy u plus v is bigger than b, i.e., so from its definition, ub of y is the supremum written above. And so for every x, the supremum is bigger than b of x minus u of x for all x. And so u and its transform also are bigger than b. So it satisfies the constraint. And on the other hand, also v satisfied the constraint. So I can take a supremum here, but that was just the definition of u conjugate. And so I've replaced v by a u, which is by a transform of u, which is smaller than v, which still satisfies the same stability lower bound, but I'm trying to minimize here. And so if I can replace v by this a priori smaller function without changing u, I do better from the point of view of this minimization. And so that's what I claimed up here. Is that clear? Any questions about that argument? So then you would think, okay, I started out with some candidate. I found this candidate does better. By symmetry, I can now apply the b tilde transform to ub. So similarly, ub b tilde ub does better still, as does ub b tilde. I could apply the b transform to this. And you might think that I can go on and on and on. And the remarkable fact is that after 3 steps, this process stabilizes. So by the time I get to here, if I keep applying these transforms over and over again, I don't get anything different than I had before. And this is exactly, so in the case b equals x dot y, this transform is what's called u star. And this is sometimes called the Legendre-Fenchel transform. And it gives you the convex dual function. Some of you may have seen this before. And now, whether or not u doesn't have to be convex to apply this transform, to apply this supremum. And what I have on the right-hand side here in the brackets is an affinely linear function of y, whether u is convex or not. For each x, it's an affine linear function of y. I take a supremum over a bunch of x's of a bunch of affine linear functions y, I get something convex. So u star is convex whether or not u is convex. Therefore, u double star is convex. U double star isn't going to agree with u unless u was convex to start out with, in which case it will agree with u provided u was also lower semi-continuous. U triple star always agrees with u star. And so this is, you know, u double star is the process of finding what's sometimes called the lower semi-continuous convex hull of a function. So the picture would be that, if you start out with a u like this, then the u double star would look like this. It's the largest convex function underneath, whose graph lies underneath the graph of u. LSC stands for convex function. And something similar is happening with these general functions B. And so my claim is U B tilde B agrees with UB. So the process terminates. And the proof is actually relatively simple. So there's 2 steps to the proof. So step 1 is to observe that from the definition, wherever it is, here's one of the definitions. Definition of UBY. Because of this minus sign here, if I have 2 different U's and one of them is bigger than the other one, the transform of the bigger one is going to be smaller than the transform of the other one because of this minus sign. So fact 1 is that U1 less than U2 implies U1 transform is bigger than U2 transform. And that's because of this minus sign. And step 2 is that UB B tilde is always underneath U. And the way to see step 2, well, UB B tilde is going to be a function of X again. It's going to be a supremum over Y. Let me write it. Let me skip 1 step. So it's going to be a supremum over Y. There'll be another supremum inside, but it will be under a minus sign. So if I move it through the minus sign, it becomes an infimum. Sorry, this should have been, this is M plus and this is M minus here. Fix that. B of xy minus B of x tilde y plus U of x tilde. That's how the B double transform is defined. And of course, one possible value of x tilde is x. And since this is an infimum, what I get is going to be smaller than what I would get if I choose x tilde equals x. And when I choose x tilde equals x, the b's cancel out. And so the thing no longer depends on y. And so that's equal to U of x. So I've just verified step 2. And then my claim follows because it now follows from the combination of steps 1 and 2. So if I take step 2, if I apply 1 to 2, I get that U B B tilde B is bigger than UB. And on the other hand, if I apply 2 to UB, I get that UB B tilde B is less than UB. And so this is one inequality and that's the other inequality, and together they imply that equality holds in the claim. Questions? Problems? Difficulties? Great. So now I know that the minimum, when this minimum is attained, I can even choose the minimizing pair to be dual functions of each other. So I now prove this claim. And these are these functions, which are dual functions to each other, are the guys that inherit a little bit of smoothness from B. So here's a definition. We say U is B convex if and only if it's its own second transform. And similarly, B tilde convex for functions on M minus. And the idea is that B convexity adapts the notion of ordinary convexity to surplus functions B other than the usual bilinear surplus. And then there's a little lemma that says something like, if these functions are all have Lipschitz constant L on X on M plus, then so does any B convex U. So I need these functions all to have the same Lipschitz constant. Otherwise, it's a bit trickier. So that's maybe part A. And part B is if they all have the same semiconvexity constant, and I can even make this local. So let me say on some subset, on omega subset M plus. And so does any B convex U. Right, and I guess I don't really mean that. I don't really mean that they all have to have the same Lipschitz constant. I want to say that if their Lipschitz constants are uniformly bounded. I.e., so what do I mean? I mean the Lipschitz constant of B of whatever Y is less than L for all Y. Is it clear what I mean? Okay. So, and again, the proof is not hard. Maybe I'll prove A and leave B to you. B is actually a little bit, I find B a little easier to prove than A, but it's a good exercise in working with semiconvexity to check the proof of B. So, so what do we want to check? When we want to check, we want to check for every X and Y in omega, we want to look at UX minus UY, and we'd like to show that it's bounded above by this Lipschitz constant L times the distance between X and Y. That's what we'd like to show. And what we know is that U is B convex. So we know that U is equal to its own second transform. And another way of saying that is that U of X is given by supremum over Y of BXY minus the transform. So I'm going to set v to be, define v to be u tilde, and then I can write v here, ub tilde, or ub rather, sorry. Let me use the eraser. And so they're going to be, since u is a supremum, there are lots of lower bounds for u. So there's going to be lots of upper bounds for this guy, for the negative uy. What's going to be a bit trickier is getting an upper bound for u of x. So for every epsilon, there exists y such that ux, where this is almost as big. So ux is less than epsilon plus bxy minus vy. And also lousy notation. So I should, let me rather call this argument z. And so also u of z, so this should have been z here. Also u of z, because it's defined as a supremum, is bigger than bxy minus vy for the same y as we chose for x. And then I subtract these two inequalities, and I get that this is less than, when I subtract these two inequalities, the b terms cancel out. And sorry, something, this is too good. Oh, this should have been a z here. The b terms do not cancel out. So, but the v terms cancel out when I subtract them. So when I subtract these two inequalities, the v terms cancel out, and I'm left with epsilon b xy minus b zy. And this is controlled by epsilon times the Lipschitz constant of b between x and z, because the assumption on this lemma was that we had this uniform bound on the Lipschitz constant of all these functions for each y. Doesn't matter what y is. And since epsilon was arbitrary, I'm done. Questions? So that's the proof of the first part of the lemma. I leave it to you to check the second part of the lemma. But basically what this lemma gives us is that as long as we have, if the Lipschitz constants of b as functions of x are uniformly bounded as y ranges over m minus, then any b-convex function will be Lipschitz as a function of x. And if the semiconvexity constants are uniformly bounded, then any b-convex function will be semiconvex. And so that tells us that if m plus is a manifold and we have these bounds, then the minimizers in the Kantorovich dual problem are actually Lipschitz and or semiconvex functions, locally Lipschitz, locally semiconvex functions. Sorry, VB. So confusing. Under appropriate conditions on P. And so that tells us that if we go right back to the beginning of the lecture today, when I was saying, this is the magic of one note, when I was saying, you know, we have this non-negative function, and where it's maximized, it's 0 where it's maximized, and we get these kind of conditions at the maximum on the first and second derivative, provided the u in question has first and second derivatives, we now know that it has first, second derivatives Lebesgue almost everywhere. And so as long as mu plus is absolutely continuous with respect to Lebesgue, we're in good shape for solving Monge's problem. And well, we need one more thing. What we'd like is that so just as in this bilinear case where the first order condition from being a maximum told us how y had to look as a function of x and gradient u, we would like for more general B to know whether the first order condition tells us how y has to look as a function of x and gradient u. And so we're going to assume that D has that property. And that assumption is, if you look in Villani's book, or probably other places, it's usually called the twist hypothesis. It actually goes back to Gangbo in the mid-90s and Levin a little bit later. So let's imagine, for simplicity, let's imagine both m plus and m minus are manifolds. It's not, what's really important is that m plus be a manifold. Well, let me do it that. So if m plus is a manifold, we say, and let's say, and for every y, B is, let's say, continuously differentiable. We say B satisfies twist, or maybe left twisted, or one twisted, or whatever, if and only if let's see, there's clean ways to say this. What's a clean way to say this? The map y from m minus to derivative with respect to xb of xy. So if for every x in m plus, this is a one-to-one map. I.e., dxby equals dxby prime implies y equals y prime. So this is somehow exactly what we need if we go back to that first order condition. Oh, I shouldn't have drawn the line there. If so, we'll write little y equals maybe capital Y of x p if and only if dx byx equals p. So if this map is invertible for y as a function of x and p, we'll call the inverse capital Y. It's sometimes also called it's also in some parts of the literature called the B exponential from x of p. Right. And basically, the point of this definition is that when you have that first order condition that we saw earlier, if the twist hypothesis is satisfied, then it's telling us that y is that function, capital Y of x and du of x. So I can figure out if u is differentiable at x, I can figure out exactly the location of the factory y that should be supplied by the mine at x in the Monge problem. And if I draw a picture, if I take b of xy to be, so we were maximizing the benefit. But so think about something like minus x minus y to the pth power, or any convex function of x minus y. And if I draw this picture somehow upside down, so x minus y, let's say, if this is a graph, if this is x and this is a graph of x to the p, then what this condition is telling me, so if here, let me draw a picture of u. So here's a hypothetical u. So suppose this is my u of x that's provided to me by the Kantorovich dual problem, and this is my m plus. And now I have some x naught, and I want to know which mine should that x naught supply its iron ore to. You want to take this function here, and you want to translate it around by different y's, and you want to move it up and down by different vy's. And you would hope that some translate and shift up and down of this function will make it exactly tangent to u of x by below, like this. So this is minus x minus y naught plus a constant plus v of y naught. And if you can do that, then this would be y naught over here. Then the fact that these things are tangent is, so this is, let's say this is b of x y naught plus v of y naught. The fact that these two things are tangent is telling you that the derivative of u at x naught is exactly equal to the x derivative of b of x naught y naught. And that's just the condition we saw up here. The fact that this function x minus y to the p is strictly convex when p is bigger than 1 is telling you that there's only one slope. There's only one place where it has the right slope to match against this function. And so that y naught is unique because of the strict convexity. Because p is strictly bigger than 1, the y naught is uniquely determined as a function of x. If p was equal to 1, this thing would look like the absolute value cone, and then I'd be able to slide it along u, and y naught would not be uniquely determined. And why should I expect that there's some such x naught? Well, because u is a B-convex function, because it's a supremum of things y in m minus b of xy minus vy. As long as the supremum is attained, the supremum that it attains, it's going to give you the y naught. So this picture is not only a picture of this condition here, it's also a picture of the pairs x naught, y naught that belong to the B subdifferential, right? Belonging to the B subdifferential tells you that this red graph is globally underneath the U graph. This condition up here only tells me that it's locally they're tangent to each other. And then the second order condition that we wrote down, you can also see from this, the second order condition is obviously that du of x naught is going to be bigger than d2b of x naught, y naught, because u minus b has a local minimum at x naught. So somehow that's the picture of the B subdifferential. It's also the picture of this condition that we're going to apply twist to. And so I guess I don't have that much time left, but I guess I want to state a theorem. So the theorem is that for simplicity, let's take mu plus and minus compact, be continuous and twisted, so actually continuously differentiable in the first variable. Obviously, M plus should be a manifold. And mu plus absolutely continuous with respect to Lebesgue on that manifold. And then the theorem has three parts. There exists U equal to its own second transform, so B-convex in other words, such that the mapping G given by capital Y of x dux pushes mu prime forward to mu minus. Right here, obviously, sorry, I should have said mu plus and minus are probability measures on the polar spaces M plus and M minus. Only one such map arises in this way. And point 3 is the measure gamma, which is given as the image of mu plus under the map identity cross G. So in other words, the map uniquely optimizes the Kantorovich problem. And somehow we've assembled all the ingredients that we need to prove this. I guess I have 5 minutes. Maybe it's enough time. I'm not sure. Maybe we've done enough assembling that it's enough. So let me see if I can prove it. I can prove parts of it, I'm sure, maybe all of it. First of all, are there questions about the theorem? So this is basically the theorem that says Monge's problem admits a solution, and moreover, the solution is unique, and Kantorovic's problem admits a unique solution.
There's a question in the chat.
Yeah, what's the question in the chat? Sorry. Yeah, it's C1 in the first argument. And so I was subsuming that into my definition of what it means to be twisted, because I didn't want to talk about whether it was differentiable as a function of y or not. So that's... Other questions? Great. So let's see, the proof would be that you start with Kantorovich optimizers gamma and UV equal to V transform U transform that we know to exist. And recall du of x is equal to dxb of xy holds gamma almost everywhere for every x provided x is in the domain of differentiability, and this is full mu measure. That's full mu measure by Rademacher, and since U is Lipschitz. So yes, so B is C1 in the first variable, and because things are compact, it's uniformly Lipschitz as well in the first variable, and uniformly in Y since the target's compact as well. And so basically the what's the main thing that I would need to check here? The main thing that I would need to check, so if I checked the last thing here, then that would also be telling me that that indeed G pushes mu plus forward to mu minus. And so that's the main thing I want to check. And so let me where am I going to check this? So I'm going to take fix U cross V in M plus cross M minus Borel. And then I would and I would want to intersect U cross V with probably the domain of the set of points where U is differentiable cross M minus. So I guess that's the same thing. I mean, this is the same thing. It doesn't really. Oh yes. What's the point? So and then I would want to apply, and so of course this is full gamma measure. This part set over here, as we just argued, because this is full mu plus measure. And so then I would want to check, what does the measure identity cross G when I define, so I want to use this formula to define G of X equal capital Y of X du. And then I want to say, what does the measure identity cross G push forward mu plus? How does that evaluate on this set here? And so that's the same thing as mu plus identity cross G inverse of U cross V intersect, well, in fact, let me do the intersect domain of du cross V. And so so that's basically mu plus of U intersect domain of du, and then G would have to be in V, so intersect G inverse of V. And since this is a set of full mu measure, that's mu plus of U intersect G inverse of V. And if I evaluate gamma on this, since this is full gamma measure, this is gamma of U cross V. And so what am I trying to say? So somehow I want to say that this, oh yes, I want to say that this equals that. And since this is an arbitrary rectangle, if this measure and this measure agree on every rectangle, then they agree on every set, because every set can be written, it can be approximated by a union of rectangles. Oh yeah, sorry, I've got to go back. Right, I've got to go back to this thing, this equality here holding gamma almost everywhere. So since that equality holds gamma almost everywhere, I can also intersect I can also intersect this with graph of G. And graph of G, which basically says every point, now when I intersect this with graph of G, I get that every point UV over here has to be of the form UG XX. So every point XY over here has to be of the form XG of X, where X is in domain du. And so I get that that is equal to basically G of X has to be in Y. So it's indeed, it's X has to be in U. So it's U intersect domain du intersect G inverse of V cross M minus. Y can be anywhere, provided X is in this set here. And then this is a set of full measure, and so this somehow agrees with this. Yeah, right. So since it's cross M minus, and since the left marginal of gamma is U, that then becomes M plus of U intersect G inverse of V. And so that agrees with this. So yes, so basically what I just checked was that this push forward here agrees with this gamma that we know is a Kantorovich solution. And so this push forward is a Kantorovich solution. Any other Kantorovich solution, this push forward would also agree with, so the Kantorovich solution is unique. Questions, problems, difficulties? Okay, so we managed to check the uniqueness of this. You get that G pushes forward mu plus to mu minus as a consequence. Maybe I didn't quite show that only one such map arises in this way, but in some sense that follows from the uniqueness of the Kantorovich maximum. All right, so if there are no questions, I'm going to stop the recording and we can transition to office hours for anyone that wants to come to office hours.